Morning, students. Today we are going to see in the Unit 5, the topic is torque about an axis. So in the earlier sections, we have dealt the torque about a point. So in this session, we'll deal with the torque about an axis. So when a rigid body is capable of rotating at any point about an axis, means when the force is acting at a point P on the rigid body, the force may not be on the plane of APB. So we can take the origin at any random point on the axis. That is will be given on this diagram. Okay, and then next we are going to see the torque of a force F about the O is, you know, that tau is equal to R into F. So the component of the torque along the axis of the torque F about the axis. So we should find the vector. What is it? Tau is equal to R vector into F vector. So what is the angle will be taken as 5 between the tau and AB. So the torque about AB is the parallel to the component of the torque along AB. So that is given as modulo of R cross F cos phi. And the torque is perpendicular to the axis, means R cross F sin phi. So that arc about axis will rotate the object about it, and the torque perpendicular to the axis will turn the axis of rotation. When both this exist simultaneously on the rigid body, the body will precession. One can witness a precessional motion in a spinning top when it is about to come rest, as shown in the figure. So this precision is given. So the spinning torque, how the rotation will be, and what is the force is acting, and the precision will be given. So the study of precision is beyond the scope of the higher secondary physics course. So it is assumed that there are constraints to cancel the effect of the perpendicular components of the torques, so that the fixed position of the axis is maintained. So the perpendicular components of the torque need not to be taken into the account. That is will be given. So the calculation of the torques on the rigid bodies will be only those forces that lie on the planes perpendicular to the axis, and the position vectors which are perpendicular to the axis. So that is the things will be given. So related with one problem is given. That problem is 5.10. The mutually perpendicular beams AB, OC, GH are fixed to form a structure which is fixed to the ground firmly. So one string is tied to the point C, and its free end is D is pulled with the force CF. Find the magnitude and direction of the torque produced by the force. So what is first we are going to be taken as about the points C, D, C, O and B, and about the axis C, D, O, C, A, V and GH. Okay, so with this we are going to find out this. So what is the solution means the torque about the point D is 0. So F passes through D. Torque about the point C is 0. So F passes through C. Torque about the point O is OC cross F vector and direction is GH. And B, BD cross F and direction is along GH. So the perpendicular of the distance of BD and the with the respect to the F is OC. The torque, and the second case, the torque about the axis CD is 0. So F is parallel to CD. When that is axis OC is 0, means when F intersects OC and the axis AB is 0, means F is parallel to AB. So the torque about the axis GH is OC cross F and the direction is along GH. The torque of a force about an axis is independent of the choice of the origin. So as long it is chosen on that axis itself, then it can be shown as below. So when the origin on the axis AB, which is rotational axis of the rigid body, so force is acting at a point P. So now choose another point O anywhere on the axis that will be given on the diagram. Okay, so that will be given in this diagram. And what we are going to write is the torque of the force AF about O is OP cross F is equal to O dash O plus OP into F, that is O dash O into F plus OP into F. So O dash O cross F is perpendicular to O dash O. This term will have not component along AB. So the component of O dash P, PF cross F is equal to OP cross F. That is the thing. Okay, and next we are going to see the torque and angular acceleration. What is torque and angular acceleration? Let us consider a rigid body rotating about a fixed axis. So a point mass M in the body will execute a circular motion. So about the fixed axis, a tangential force F acting on the point that produces a necessary torque for this rotation. This force F is perpendicular to the position vector of the point mass. The picture is clearly given. What is given and how it will be, that will be given in the picture very clearly. The torque and the angular acceleration. So the torque produced by the force on the point mass M about the axis can be written as tau is equal to RF sin 90, that is RF when 90 is equal to 1. Then RMA, F is nothing but MA, RMA. And what is that MA? A is nothing but R into alpha, that is angular. A is equal to R into alpha. So R into alpha, what is that? Final equation is tau is equal to mr square alpha. So the torque of the force acting on the point mass produces an angular acceleration alpha in the point mass about the axis of rotation. So in the vector form it will be written like this. So direction of the tau and the alpha are along the axis of rotation. If the direction of the tau is in the direction of alpha, it produces angular acceleration. On the other hand, if the tau is opposite to the alpha, the angular deceleration or retardation is reduced. So you know what is given. So if both will be on the direction of the tau and the F is same, means it produces angular. On the other hand, it is opposite, means it will produce the angular deceleration. So the term mr square, that is called moment of inertia of the mass. A rigid body is made up of many such points. Hence, a moment of inertia of the rigid body is sum of the moments of inertia of all such individual point masses. So the constitutes the body I is equal to summation of mi ri square. Torque for the rigid body can be written as tau is equal to summation of mi ri square alpha, that is equal to I alpha. We learn about the moment of inertia and its significance for the bodies for the different with the different shapes. And next we will go pass on to the angular momentum. The angular momentum in rotational motion is equal to the linear momentum in the translation motion. So the angular momentum of the point mass is defined as angular momentum of the linear momentum, the moments of a linear momentum. In other words, the angular momentum L of a point mass having a linear momentum P at a position R with respect to a point mass or axis is mathematically written as L is equal to R cross P. The magnitude of the angular momentum could be written as L is equal to R P sin theta. Theta is the angle between R and P when L is a perpendicular to the plane containing R and P. So we have written in this case the torque is nothing but, and also we associate the sin theta and the R and P. So L is equal to R into P sin theta, that is R into P perpendicular, and L is equal to R sin theta P, that is R perpendicular into P. When P perpendicular is a component of linear momentum P perpendicular to R, and R perpendicular is a component of the position R perpendicular to P. the angular momentum is 0, that is L is 0, linear momentum is 0, P is equal to 0. Or if the particle is at origin R is equal to 0, then if R and P are parallel or anti-parallel to each other, that is theta is equal to 0 degree or 190. There is a misconception that the angular momentum is a quantity that is associated with the rotational motion. So, the angular momentum is not associated with the bodies in the linear motion that is given. So that will be understand the same with the following examples, and that is given here. So example problem of 5.1 will be similar to these things. When a particle of a mass m is moving with the constant velocity, what is the angular momentum about any point remains the constant throughout the motion. So the diagram is given clearly. Let the particle of the mass m move with the constant velocity v. As it is moving with the constant velocity, its path is straight line. Its momentum p is equal to mv is also directed along the same path. Let us fix an origin O at the perpendicular distance d from the path. At the perpendicular distance, we can connect the particle which is at the position of q with the position vector, that is r is equal to q OQ. So the angle between the r and p is theta. The magnitude of angular momentum of that particle is that instant is equal to L is equal to OQP sin theta, that is equal to OQ mv sin theta, that is mv into OQ sin theta. The term OQ is perpendicular to the distance d between the origin and the line along which the mass is moving. Hence, the angular momentum of the particle about the origin is L is equal to mvd. So, in the above expression, the angular momentum L does not have the angle theta. So, the momentum P is equal to mv, and the perpendicular distance d are constant, so the angular momentum of the particle is also constant. The angular momentum is associated with the bodies with linear motion also. If the straight path of the particle passes through the origin, then the angular momentum is 0, which is also a constant. Next, angular momentum and the angular velocity. Let us consider a ridged body rotating about a fixed axis. A point mass m in the body will execute a circular motion about the fixed axis. So that will be given here, and the point mass m at the distance r from the axis of rotation, its linear momentum at any instant is tangential to the circular path. Then the angular momentum L is perpendicular to r and p. Hence, it is directed along the axis of rotation. So, the angle theta between r and p in the case 90 degree, the magnitude of angular momentum L could be written as L is equal to r mv sin 90 degree. That is equal to r mv, where v is a linear velocity. The relation between the linear velocity v and angular velocity omega is given as v is equal to r omega. And the next thing is L is equal to r m r omega is nothing but L is equal to m r square omega. So the direction of the L and omega both will be axis of rotation. So when the expression given in vector form, that is L is equal to m r square omega. So the term m r square in the equation, both the equation in 5.2 and 5.23, that is moment of inertia of the point mass. A ridged body is made up of many such point masses. So the moment of inertia of the ridged body is sum of the moments of inertia of all the individual points masses that constitute the body. That is that I is equal to summation of mi ri square. The angular momentum of the ridged body can be written as L is equal to summation of mi ri square omega, that is I omega. So this I is nothing but moment of inertia. Next, the torque and the angular momentum. We have the expression for the magnitude of angular momentum, same, that is L is equal to I omega. So the magnitude on the torque will be tau is equal to I alpha. So write the expression as That means we are going to change these two equations. Tau is equal to I d omega by dt. Therefore, alpha is equal to d omega by dt. And omega is angular velocity, alpha is angular acceleration. So, we are able to write this equation as tau is equal to di omega by dt. I omega is nothing but L. So, that is tau is equal to dl by dt. So, this expression says that external torque on the rigid body fixed to the axis produce a rate of change of angular momentum in a body about the axis. Second law rotation in motion is in the form of F is equal to dp, which holds good for the translation motion. So that is given here.